The world is now battling a terrible epidemic. The current pandemic has changed and disrupted our lives in many ways. In order to fight any epidemic, we need to first understand its mechanics and dynamics. And this is where mathematics comes in. In this video lecture, we discuss how mathematics, and in particular difference equations, can be used to model epidemics and help us better understand the spread of diseases. Hello everyone, my name is Ang Keng Cheng, and I'm an associate professor at the National Institute of Education, which is a part of the Nanyang Technological University in Singapore. This video lecture is outlined as follows. First, I will introduce the idea of difference equations. We will briefly discuss what these difference equations are and how to use a tool like Excel to generate values through the recurrence relations obtained from these equations. Then we look at a couple of examples to reinforce this concept. Next, we will take a look at what mathematical modeling is, the process, the stages, the modeling cycle. Some key terms used in mathematical modeling will also be introduced. Finally, we will study two simple models often used in studies of epidemics, the SI and the SIR models, constructed using difference equations. Again, we will use some numerical examples to demonstrate how we can obtain graphical solutions to these models. Excel will be used in these examples. Take a look at this sequence. We know that this is a sequence of odd numbers starting with 1. We can write down the terms as A0 equals to 1, A1 equals to 3, A2 equals to 5, and so on. Notice from this pattern that the difference between successive terms is always 2. In other words, we can write down or say that the difference between an plus 1 and an is 2, or an plus 1 minus an equals 2. This is called a difference equation. We also note that we can rewrite the same equation as an plus 1, the next term, equals an, the current term, plus 2. So to find the next term, we take the current term and add 2. Written this way, we can continually generate the next term if we know the value of the current term. The formula repeats itself, or we say the formula is recurring. So we call this a recurrence relation. So using this concept, we can define a difference equation. Difference equation is a mathematical equality involving differences between successive values of a function. Difference equations can be very useful. For example, we can use them to model certain dynamical systems like changes in salmon populations in a habitat, the growth of your money placed in some bank with some compounded interest, or the spread of diseases and epidemics, something that we're going to discuss in this video. Solving a difference equation, however, is not always trivial, especially if we want to have a closed form formula as a solution. Fortunately, given a difference equation, we can write it as a recurrence relation. And if we can do so, we can generate successive function values using a computing tool such as Excel. But first, let's try some simple examples to make sure we know how to use a spreadsheet to generate these function values efficiently, and perhaps also to plot a graph of these values. And this is how we will be approaching it here in this video lecture. Let's look at example 1. We have a very simple difference equation, an plus 1 minus an equals 2, and the first term is a naught equals to 1. We saw this earlier. This is a sequence of odd integers starting from 1. Well, in this particular case, we can actually solve the equation. Now, if an plus 1 equals to an plus 2, then we can replace an by an minus 1 plus 2. So that now an plus 1 is an minus 1 plus 2 plus 2. Similarly, we can replace an minus 1 by an minus 2 plus 2. And we can do this recursively until we reach a naught. It is not hard to see that in the end we will get an plus 1 equals to a naught plus n plus 1 times of 2. But if we want to generate individual terms, we can do so recursively using the recurrence relation with the starting term. Let's see how we can do this and plot a graph of the generated values using a computing tool. Let us demonstrate this using Excel. In this example, let us consider the difference equation given here, an plus 1 minus an equals to 2, with a starting value a naught equals to 1. Now we would like to generate a sequence of values using this difference equation for an, but we can write it down as a recurrence relation given by an plus 1 equals to an plus 2. In other words, the current value is equals to the previous value plus 2. To generate these values, we could set up a worksheet like this one, where we have one column here to record the values of n. So n will start from 0, 1, 2, and so on, and the corresponding values of an in the other column. So the first value of n is 0, and when n is 0, we have a naught. A naught is given by 1, and this is the given starting point. Now, so what we're going to do in this column A is to generate or to produce a list of values for n. So n goes from 0, the next value is 1, the next value is 2, and so on. We could type everything down, or we could use the fact that these two numbers here, n equals to 0, n equals to 1, there is a pattern which is 2, 3, 4, and so on. So in Excel, if you were to highlight these two values here and there's a pattern moving down, we could generate the list of values by highlighting the two cells and then placing the cursor in the bottom, at the bottom corner. And you notice that the cursor turns to a crosshair. We can then left click, hold, and drag it down to where we want to stop. In this case, 12. So to generate the values of an from a1, a2, and so on onwards, we could write down the formula for it in this cell. For example, in cell B5, we put down equals the previous value plus 2 according to the recurrence relation. Hit enter, and that gives us the value 3. Now because the formula is now written here, we can just copy the formula downwards and generate the entire set of values for n equals to 1, 2, and so on up to n equals to 12. Now we can plot a scatter plot or construct a scatter plot for this set of values. First, we highlight the two columns, and then we go to Insert, and we choose under Charts, Scatter. There are a number of different types of scatter plots, but in this case, we want to have just markers, scatter plots using just markers. So actually, we are done. But we could perhaps customize this plot a little bit. course, there are other elements that we can continue to customize, but that will do. In this case, we have already constructed or created the list of values using the recurrence relation and constructed a simple scatter plot. Here's another example. The difference equation is given by an plus 1 minus an equals some number r multiplied by an. The starting value is 1000. Or we can write down the recurrence relation as an plus 1 equals to an plus r times an. This equation can be used to model, for instance, the amount of savings over a period of time, starting with some initial principal amount and given some interest rate. This difference equation, again, can be written as a recurrence relation. An plus 1 equals an plus r times of an. And like the previous example, this one can be solved easily, as shown here. Similarly, if we want to generate individual terms and see how the value of an changes at each stage, we can use a computing tool to generate these values and plot its graph as well. Let's see how this can be done in the following demonstration. In this example, we look at the difference equation given by an plus 1 minus an equals to some factor, let's say r, multiplied by an. So in other words, if we were to write it down as a recurrence relation, it will look something like this. An plus 1 equals to an plus r times an given some initial value starting point a0. So for example, in this case, a0 is 1000 and the r given here is 0.050. So we can use a spreadsheet like Excel to generate the values and maybe plot a graph, a scatter plot, to see how it looks like. So in this case, we have set up here two columns n and an to store the values. So let us generate the values in the first column for n first, and we look at the rate r or the factor r a little bit later. So in this case, I want a whole column of numbers increasing by 1 is to act as something like a counter. So 0, 1, 2, 3, and so on. So we have done this before. We start with 0 in the first row, and then we have 1 in the next row. Okay, we start with 0 and 1, and there is a pattern now, and we can then copy down. So we put a cursor right at the corner here, and it turns into a crosshair. Hold, click and hold, and then we drag down all the way down until we reach the point we wanted, which is 100 here, right? Now, in the second column, we're going to use this formula here to generate the column of values. Now, instead of, and we know that if we use this formula, we will need to make use of this value here, which is at the moment given as the address B1. But we might like to give it a name. So to give it a name, we right-click and go down to define name. So in this case, let's call it rate. And the scope where this name applies, maybe we just restrict it to this particular worksheet called example 2. And we say, okay. So now within this worksheet, rate is now known to be associated with this cell, B1. So we start by now generating the values equals to whatever that's previous plus the rate multiplied by the previous. So you can see the formula that is written. We enter. Once we have the formula, we can then copy this formula and fill it down. So the fastest way is to put the cursor at the corner here and double click. And you can see that it's all filled down all the way to 100, to where the corresponding value stops. So we can then similarly generate a plot of these values. Right? Insert. Now we're going to use a scatter. That's what we've done before. Right. So maybe we first of all we increase the fonts a little bit and maybe make it bold. And we can see what happens when we change the rate, let's say to 2.5%. Or if we can increase the rates to 7.7%. And you can see the difference and so on. Before we continue to discuss how difference equations are used in modeling epidemics, let's take a brief look at what mathematical modeling is. What is mathematical modeling? In mathematical modeling, we begin with a real-world problem. Our aim is to find a real-world solution, and we hope that through mathematical modeling, we are able to achieve or obtain this solution. In real life, however, very often the solution to the problems is often one that would help us make some decisions or make predictions about something or some event. Sometimes we may not even get a solution, but we hope to understand certain phenomena better or explain why or how some things happen. And sometimes we could only hope to gain better insights into the problem that we are studying. So in other words, while a solution is what we hope for, the outcome of mathematical modeling could be just further or deeper understanding of the real-world problem. Put simply, mathematical modeling then is a process of representing or describing real-world problems using mathematics, so that we may find solutions to the problems or at least gain a better understanding of the problems. Mathematical modeling usually begins with a real-world problem, and we hope to find a real-world solution by making use of mathematics. As a first step, we try to think of the real-world problem in mathematical terms and formulate a mathematical problem. This step usually involves identifying the factors or variables in the problem and going through some form of abstraction of the problem before formulating a mathematical problem. Once the mathematical problem is more or less defined, we could then see if we can simplify it by making certain assumptions about the problem situation. We could, for instance, specify the boundaries of the problem, or if this is a first attempt, reduce the scope of the problem. For instance, mathematically speaking, if we are dealing with space variables, we could think about whether it is possible to consider a one-dimensional situation first, at least for a start. Given these assumptions then, we may now try to construct a mathematical model. A mathematical model is simply a mathematical construct that helps us solve the mathematical problem that has just been formulated to represent the real-world problem. It could be an equation, a table, an algorithm, a set of rules, or even a diagram. The next stage is to solve the model. By this, we mean that we could employ some suitable method or technique
based on the mathematics that we have just used to obtain some output or outcome of the model that we have just constructed. For instance, if the model is an equation, we could solve the equation. If the model requires a computer simulation, we could perhaps write a program to find the outcome. After solving the model and obtaining the solution, we should now try to relate the situation or the solution to the real world by interpreting the solution in the context of the real world. In so doing, we would try to see if the solution makes sense or whether it's reasonable or appropriate. If we have access to data or any other information that could help us determine the suitability or appropriateness of the model, we would use them to validate the solution. Validation could be in the form of comparing the results of the solution with known data or examining the qualitative behavior of the solution in relation to the real situation. It is possible that arising from this validation or checking process, we find that we need to revisit the assumptions and to refine the model by modifying or changing some assumptions. This part of the process is called model refinement, and we can continue to refine the model until we are satisfied with the final model. In general, there are three common approaches to mathematical modeling. A model that is based primarily on empirical data collected is called an empirical model. A model that is constructed by examining the dynamics of a problem situation to determine an outcome is called a deterministic model. Using rules and algorithms to control the flow of events would result in a simulation model. An example of empirical modeling is the stopping distance model. Here's a set of data showing the speed of a car and the distance it comes to a halt when the brakes are applied suddenly. It can be seen that at higher speeds, the car will require a longer distance to come to a complete stop. But can we find the relationship between the speed and the stopping distance? Let us focus on the relationship between the stopping distance shown here in the vertical axis and the speed of the car in the horizontal axis. From the data points, it looks like the data can be fitted using a quadratic function. This function is then a model that describes the relationship between these two variables. In deterministic modeling, we look at the dynamics of a system. As an example, consider the spread of a communicable disease. Let us assume that the population in a community consists of susceptible, infected, and recovered individuals. It is reasonable to suggest that a susceptible individual can get infected by being in contact with an infected person, and then an infected person may later recover and become immune to the disease. Based on this relationship, we may then write down a set of differential equations to represent the interactions and hence determine how the disease might progress. And so here are the equations. Solving these equations numerically with given conditions and parameter values results in this typical behavior of the three compartments of the population. Incidentally, this model is called the SIR model for epidemics. To illustrate simulation modeling, consider this situation. Suppose we roll 2 dice and add the 2 outcomes. So we can get values of the sums ranging from 2 to 12. Now, if we want to find the distribution of these sums, we could do so experimentally and physically by rolling a pair of dice many times and finding the frequencies of each possible sum. But that would take too long. This is where we could set up a model to simulate the rolling of 2 dice and then find the resulting distribution. One way to set up such a simulation is by using a spreadsheet with computing or programming capabilities like Excel. And here's a short video clip to show how a simulation model can be set up. A random number generator is used to simulate the rows of dice. With the code that we've written, we can do this many times very quickly. Find the sum, and then count the number of occurrences of each sum to draw up the frequency table and plot the frequency graph.
Now that we know something about modeling, we are ready to discuss some fundamental models used in the study of epidemics. Imagine we have a closed community as shown here. The individuals in this community stay within the boundaries. Suppose there is one infected individual as indicated by the pink dot, while the rest, indicated by the green dots, are not infected but they are susceptible individuals. That is, they are not immune, but they can be infected. In a typical setting such as this, if the infection is transmissible through interaction between individuals, then there is always a chance that more will become infected. Assuming that the population within this closed community is well mixed, the phenomenon of mass action interaction will lead to even more infections. And this is how the disease will spread. Schematically, we may represent the situation as having two subpopulations. One is the susceptible subpopulation, and the other is the infected subpopulation. Individuals move from being susceptible to being infected in this one direction. This is the basic susceptible infected, or the SI model. It is an example of a compartmental model, as populations are grouped into compartments and individuals move from one compartment or group to another. Here are some basic assumptions of this model. First, we assume that the populations or the individuals in the populations are well mixed. The condition of mass action interaction exists. That is, the individuals are not isolating themselves. We also assume no births or deaths occur during this period under question, and also no disaster or major catastrophe happen to cause deaths. The community is assumed to be closed, and so there are no immigrants or emigrants. And we also note that this further implies that the total number of susceptible individuals and infected individuals at any time remains unchanged. Let's look at the situation mathematically and construct a mathematical representation of the situation. Let Sn be the number of susceptible individuals at some time point n. Similarly, In is the number of infected individuals at time point n. Suppose we focus on the number of infected. The change in infected numbers, or difference between the number of infected at the next time point n plus 1 and the current time point n, depends on the transmission between the susceptible individuals and infected individuals through some mass action interaction, some probability or rate of transmission represented by B, and the time step given as delta t. Mass action interaction in this case can be represented by the product of S and I, population numbers at time point n. So this is the difference equation that we obtain. But we note that if we assume the community to be closed, then at any time point n, Sn plus In must be a constant. And we let this constant be capital N. So now we have this difference equation, In plus 1 equals to In plus delta t times b times Sn times In. And we know that Sn plus In equals to some capital N. This means that Sn is equals to capital N, take away In. Substituting and rewriting, we obtain a form of recurrence relation given by this last equation here, which is In plus 1 equals to In plus delta t times b times n times In into 1 minus In over capital N. We can simplify things a little. Suppose we take the time step as 1. That is, at each time point, each time point differs from each other by 1 unit, whatever this 1 unit may be. And if we let R be b times n, b times capital N, then the equation can be written as In plus 1 equals to In plus R times In into 1 minus In over capital N, given some I naught. This is the equation for the SI model in discrete terms. In fact, this equation has a name. It is the discrete form of the logistic equation. And in this case, the value N is known as the carrying capacity of this model. Let's try a numerical example and see how this works. In example 3, let us suppose that we have R equals to 0.25 and we need to plot the graphs of the infected population against time t. We shall assume various different values of the starting infected number, I naught. This is the initial value for I. We may then vary I and see what happens. Let's use Excel again and demonstrate how this can be done very quickly and very easily. In this example, we will demonstrate how an Excel worksheet can be used to plot the graph of an infected population against time in an SI model. This worksheet that you see here has been prepared with the usual setup: the columns of values required, the value of parameter R, and the plot area containing the graphs. This is the formula that we will use to generate the graph. Also, we have earlier defined or named the cell B1 containing the value of R as rate 1. We have set up a number of columns here to store the values, as well as customized the look of the graphs in the plot. In the first column here, we will put in the time points. These are in arbitrary units. Let's say we have 60 time points. The first step is to fill this column with the time points. We start with 0, and the next one is 1. And the next one is 2, and so on, incrementing by 1 unit. We have done this before in earlier examples, and we can do this very efficiently and very quickly. In the next few columns, we will generate the values of the infected populations using this formula here with different starting or initial values. For instance, in this column B here, the initial value is I naught equals to 2. So the next value, I1, will be equals to its previous value plus rate 1 multiplied by the previous value multiplied by 1 take away the previous value divided by the total number in the population. Say, let this be 100. So we obtain a value 2.49. We can then copy this formula to the next two cells for the corresponding next values with different initial values. We can then copy all three formulae down to the end of the time scale that we have set for ourselves. And the graph is plotted. The plot of these graphs has been set up earlier using the concepts and methods that we have learned in previous examples. At the end of example 3, we now have a sense of what the SI model is. We know how to implement the model on an Excel worksheet, and we know what the solution might look like. Depending on the values of the parameters such as the rate of transmission, the initial number of the infected individuals, the carrying capacity, or the total number of individuals in a closed community. Incidentally, the graph of IN that one obtains from the logistic equation is also known as the sigmoid curve, and it has the characteristic S shape. The SI model is often used and applied in highly contagious and communicable diseases, especially over short periods of time where intervention measures or quarantine policies or vaccinations do not happen fast enough to contain it. An example is the SARS outbreak that we experienced in 2003. As an extension of the SI model, we could consider another compartment. That is, people who got infected may recover. So we can include the recovered or the R compartment in this SIR model. The same basic assumptions as before shall apply. That is, closed community with no immigrants and emigrants, no disasters or catastrophe, and individuals are well mixed and interacting with one another. In addition, we assume that an individual who has been infected and has recovered will neither be susceptible nor infectious. This SIR model is also known as the Kermit-McKendrick model. The difference equations written in the form of recurrence relations for the three subpopulations are given as shown here. Sn plus 1 equals to Sn minus delta t times b times Sn in. In plus 1 equals to In plus delta t times b Sn in minus Rin. And finally, Rn plus 1, the recovered population, is equals to Rn plus delta t times R times In. Here, B represents some rate of transmission, and R is a measure for the rate of recovery. Obviously, we have to begin with at least one non-zero positive value of I, and the initial value of R should be 0. Again, closed community requires that S plus I plus R equals to some constant. These equations will have to be solved simultaneously, and each value of S, I, and R is to be computed at each time point before values at the next time point can be computed. Once again, it is convenient to use a spreadsheet or Excel, in our case, to solve this model. Because all variables including the parameters b and r are positive, it is obvious that over time s will decrease and r will increase. Looking at the equations, obviously if b, the rate of transmission, is large, then it means that the second term on the right hand side of the first equation for s will be large. This means that the susceptible numbers will fall more rapidly if b gets larger. This makes sense. Now, if the rate of recovery r increases, then the second term on the right hand side of the third equation, that is the equation for r, will increase as well. And this means that the number of recovered individuals rises more quickly. The rate of recovery goes up, r goes up. This also makes sense. The second equation representing the infected numbers has a right hand side that is influenced by both parameters b and r. So it may not be immediately obvious what kind of graph it will trace out or how it will behave over time. However, intuitively, we can imagine that the number of infected individuals typically starts small, then rises to some peak representing an outbreak, and then it will fall because individuals recover and there will be fewer and fewer susceptible individuals in the community to be infected. Let's try this out with a numerical example. Example 4. We let r and b take some arbitrary values, and s, I, and r to be given some initial values. Again, let's use Excel to generate the graphs. In this example, we look at how the SIR model can be implemented on a simple Excel worksheet. So these are the three formulae for the recurrence, or the three recurrence relations for the subpopulation S, I, and R, susceptible, infected, and recovered. And notice that in here we have delta T and B as well as R as the parameters. So here we have set up B, R, and DT as the values for B, R, and delta T here. So we have previously already set up this worksheet so that this cell here, B1, is referenced by the name rate B. And the cell here, B2, containing the value of R, is has the name rate R, right? And the cell B3 containing the value of delta T has the name dt. The initial values of S, I, and R are stored here. And on the column D here, we store the values of the time in days. This graph here has already previously been set up to plot the graphs of SIR given in this column S, column E, column F, and column G. So now what we need to do, all that we need to do is to generate the values. Now this column for time T has already been previously set up to contain values from 0 to 100. So given these initial values, then we can make use of this formulae to generate those values. So for example, for S will be equals to the S1 will be equals to S naught, right? Take away dt, already defined, multiply by rate B, multiply by the previous value of S, and multiply the previous value of I. Okay. For I, the formula is equals to the previous value in plus dt times brackets rate B times a previous value of S times the previous I value minus rate R times previous value of I. We close the bracket, and that should give us the next value for I. Of course, at the moment you don't see much change. Similarly, for R, we use a formula R equals to R plus dt times rate R times the previous value of I. So now that we have the formulae that is already defined for these three, we can copy down all the way till we reach the desired time point here. And the values are given there, and we find that the graph is, as we have earlier on set up, is plotted. And this is how we can make use of a simple worksheet to generate the values or generate the values of S, I, and R in order to have a sense of how the populations will change, the subpopulations of S, I, and R will change over time in this epidemic. So as we can see, S will start from the susceptible numbers will drop, right? As the infected number increases, and then it will peak somewhere and comes down. And given that there is good recovery, the recovered numbers will increase. So here we are, the typical graphs of the susceptible, infected, and recovered populations in the SIR model. This model has also been applied to model epidemics in the past and has been quite successfully used. One example is the use of this model in studying the flu epidemic that happened at a boarding school in England in 1978. But of course, as always, the challenge in these applications is the choice and estimation of the values of the parameters in the model. In summary, in this video, we have seen how simple ideas in mathematics supported by a simple computing tool can be effectively used to represent some real-world situations. Of course, in real life, things can get very complex, and using difference equations or just Excel may not be enough. Nevertheless, I hope this video with simple examples has achieved its objectives of showing what is possible and what mathematics can do in modeling epidemics, bringing us one step closer towards solving a real-world problem.